Hello there, cutie patootie math angel. Yes, even you. Welcome back. Welcome back. And a very warm welcome if you are new around here. This is Decaf-Math ASMR. And thanks for joining me today. I hope that this is finding you well. Today, I thought that we could chat about finding the inverse of a function if it exists, and nothing really planned. We're just gonna see what comes up and take it nice and slowly, and down the line we can always come back and fill in some gaps or do extra practice problems, but there's no rush, no rush, no rush. So I hope that this is helpful if you're actually learning this. Maybe it makes for some nice review, or maybe you learned it a long time ago but never really got to the point where you felt confident with it, or maybe you don't really care, whatever the case may be. You can also just sit back, close your eyes, relax, 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 and just let the math wash all around you, okay? All is okay. All is well. All is okay. All is well. I'm just so glad that you're here with me right now. And let's just jump right into it, okay? Okay, so before we talk about an inverse function, let's do a little bit of review about how functions work, okay? So let's start with a more basic function, a linear one for now, just so that we can build some intuition slowly. And then, of course, you can extrapolate everything that we do today to other kinds of functions as well, okay? So let's start with a linear one. How about something like this? F of x is 2x minus 1, okay? So this is a linear function because it has this form, some number m times x plus b, or minus a number, okay? So this notation just says it's a function of x. So if I read this out loud, it looks like, well, if I look at this on a piece of paper or something, it's just mumbo jumbo. But if I read it out loud, it's a function of x is 2x minus 1. Okay, so this is a function of x. That just means that if I give you some sort of input, my x is just a placeholder. I know it's kind of boring, but you can kind of replace it with something else logically, okay? So it just means I give you something. This is my set of instructions for what to do with it to give you a corresponding output. So if I give you a particular value, okay, for x, then this says do 2 times that x, whatever that is, and then subtract 1. And you do the 2 times first and then the minus 1 because of order of operations. So that's the PEMDAS or BEDMAS or whatever acronym you might have learned for that, but multiplication first and then subtraction because there's no parentheses or anything here, okay? So it's just a little game. Input, output, input, output. So usually what we'll have here is it says a function of x, but usually we'll have another variable. Let's just go ahead and put a y. So y and f of x are usually used interchangeably, but conceptually they're slightly different, and usually you'll use the y is 2x minus 1 for when you're graphing or something like that. But conceptually, it's the same like idea, right? So deep down, it's y is a function of x. So this kind of gives you more information about this variable. So x is my input variable, so it's independent of anything else. So as long as I'm giving you input values that, don't break the math here, meaning you don't want to divide by 0, you don't want to take square roots of negative numbers in the real realm, you don't want to, take trig functions of stuff that's not in the domain, that kind of thing. That word domain we're going to come back to, but as long as you pick inputs that are actually valid for your function or your set of instructions, then it's just independent from anything else. You just pick it, right? And then once I set that input, my output, my y value, is completely dependent on that because it takes that thing and then does stuff with it. So times 2 and then minus 1. Okay, so y is my dependent variable, x here is my independent variable. Okay, so that's it. Functions are just sets of instructions to give you corresponding outputs, and then there's a specific property that needs to happen, which is that with any particular input that I give you, so let's say I give you the value 0, okay? There needs to be, in order for this thing to actually be a function, there needs to be exactly one output that corresponds to that input, okay? So what would happen if I gave you a set of instructions and sometimes 0 would map to 1 and sometimes 0 would map to 5 and then other times it's 3? That would be really confusing to work with, right? For this kind of analyzing, because how do you know when? So you want clear instructions. So if I feed you 0, in this case, it says 2 times my 0, which is 0, minus 1, so that would be negative 1. Clear, straightforward, give you 0, you give me negative 1. Okay, so that's all that is. If you've learned this before, this might kind of ring some bells for the vertical line test. So when you graph a function on the xy Cartesian coordinate plane, you'll have a picture. In this case, it'll be a line. And so the vertical line test is basically the graphical version of what we just said, which is if I draw vertical lines anywhere on my graph, it should only ever intersect my graph at one point, because the vertical line is where x is a constant or a particular value. So as I trace up or down following the y values, there should only ever be one that touches it. So that's the vertical line test. And so in order for something to be a true function, you shouldn't have something like, like this S pattern or anything kind of that doubles up over itself in a graph. Okay, so that's what a function is. And so now what we can do is kind of make a table of certain values just to get an idea of how this function works. So I can have particular values that I want to set just out of curiosity for an input side, and then corresponding outputs. And for a continuous thing like this, like we know the graph of this is going to be a straight line, there are infinitely many little points along a line, so there's no way to actually make a table of all the possible values, right? X values don't have to be integers, right? So there's just going to be infinitely many inputs I can put in, but a table can help us get a feel for the pattern and the shape of our graph, and it's just cool to think about. So why don't we just kind of start looking at a table for this and then use that for intuition for our inverse of this function. So what I'm going to do is make a little table, but I'm going to use washi tape because washi tape is just so cute. It's so nice. It's sticky, but it's not too sticky. So anything to make things a little cuter around here. Alright, so this is my wall, okay? And it divides my input and my output. So my input side is going to be X, and my output is going to be Y. Okay. And here's my wall. So in order to go from here to here, it's like our secret code, okay? In order to jump from here to here, I use this function, 2x minus 1. That's my instructions. Whatever I do here, multiply by 2, then subtract 1. Okay, so you ready for this? I'm going to give you a value and you're going to tell me the output. So I'm going to give you -1. I know I start with the negative. What a pain. But so I'm going to take 2 times that -1 and then subtract 1. Now, I'm not going to make you do that in your head in case you're trying to actually relax and sleep, but I'm going to give you a chance to do it. So 2 times -1, a positive times a negative is negative because they're different signs. One's positive, one's negative. So you're going to have -2 minus 1 is -3. Good. Okay, so if you're not comfortable with negative numbers, don't worry. You can check out my other videos or let me know if you want to do this some more, but just take my word for it for here. Okay, so this is 2 times -1. Put in parentheses to clarify that we're multiplying and not subtracting. So you do that first to get -2, and then you subtract 1. So -2 minus 1 is -3. Good. So input's -1. I use our little secret code to jump over the wall to get -3. Good. So now let's put another input. And these are just arbitrary values. Usually if you're kind of sketching graphs and stuff, you'll pick, nice integers just because it's easier to plot and write out a scale. But you want to do a little bit negative stuff, maybe a little bit 0, maybe a little positive stuff, but whatever it takes to get a feel for this function. So 0 is nice. 2 times 0 is 0, and then -1 is a -1. 0 minus 1 is -1, right? So 2 times 0 is 0, minus 1 is -1. So then 1 would be 2 times 1 is 2, minus 1 is 1. Excellent. Very good. And how about one more? So 2 would be 2 times 2 is 4. 4 minus 1 is 3. Excellent. Very nice. Oh, okay. If you insist, let's do one more. So 3. 2 times 3 is 6. Minus 1 is 5. Good. Okay, so now we have a bunch of pairs. So if I give you -1, you give me -3. If I give you 0, you give me -1. If I give you 2, you give me 3. That kind of thing, okay? If I give you heart, you give me 2 heart minus 1. Very good. So now we have like this mapping. This function is really just taking values and sending them over here. And like we said, all we expect is for each of these values to go to exactly 1. So I shouldn't have -1 maps to -3 and -1 maps to 5. Otherwise that wouldn't be a function, okay? But theoretically, for right now, technically speaking, not for this particular function, but technically speaking, two different inputs could theoretically map to the same output. That is okay because that still fulfills our definition of each one input mapping to one output. It just so happens that two different inputs map to the same output. That's okay because the output's still clear, right? Okay, for now. So now what we're going to try and do for the inverse is to go the other way, reverse it, right? So going here is this way, but if I want to send a secret code back to you to go from -3 to -1 and -1 to 0 and 1 to 1, we're going to reverse. Okay, so this is actually going to be quite fun. So how this works is basically we're going to flip-flop our x and y. So back to the original question, it was find the inverse of f of x is 2x minus 1. So the first step is put in a y. Okay, so you have y equals 2x minus 1, or whatever function you have. The next step is to flip-flop x and y. I mean, there's lots of ways to think about this, but this is usually the most straightforward to do way of solving it. But intuitively, to go from here to here, my y's are now going to be my inputs for this inverse function that we're going to find. So my y's going to become x's and my x's become y's. So naturally, if I flip-flop these values, I will kind of be closer to my inverse. So instead of y, I have x, and then instead of x, I have y. So literally flip-flopping these values. Now these two equations are not equivalent. That's why I made a note here that I am flip-flopping. I don't want to just randomly have things on my paper without being clear with what I was doing. These are not equivalent, but it's a step that I'm going to take to solve for my inverse. So I flip-flopped it. Now what I'm going to do is, well, this is technically my inverse function already, but it's in terms of y. So instead, I'm going to solve for y in terms of x here. Okay, so I'm just going to use algebra and do whatever I can do depending on what the function is. In this case, it's going to be like linear steps, right? But I'm going to isolate this y and do y equals something with only x's in it. Okay, so let's do that. Take your time with these steps if you're not familiar with it. I'll do the work here, but in this case, I want to leave y on one side, so I'm going to get rid of this -1 first by adding 1 onto both sides, if you want to think of it that way, or just moving this -1 over. And that's so that this becomes 0, which is an additive identity. It becomes 0, so it goes away. So I have x plus 1 is equal to 2y. Okay, and now I still want to isolate this y, and it's 2 times y, so to undo that multiplication, I'm actually going to divide by 2 to get the multiplicative identity, which is 1, so that 1 times anything is itself. But if I do it on this side, I have to do it also onto this side. And note that it's the entire thing x plus 1 divided by 2, right? So I want to make that clear. I'm not doing x over 2 plus 1, or it's x plus 1 divided by 2. So now I have y equals, so now I've accomplished my task. I have isolated this y now, and on this side I have x plus 1 over 2. And if I'm just working with this algebraically, I can leave that as is. It's perfectly fine. If I'm going to be working with this like with a graph or something like that, it probably helps to write this as an mx plus b form, which is to distribute this divide by 2 here. So I might do something like this, 1.5, make sure the x is to the side, or just do 2 plus 1, any of these are okay. They're all equivalent, okay? But now that is my inverse function. So to actually complete the question, I will want to write, instead of this y thing here, I want to actually answer the question, like what is the actual inverse function. I want to write this as f inverse x. Okay, let me make sure that this notation is clear here for you. So we have x plus 1 over 2, or any of these, any of these equivalent ways, but let's just remember x plus 1 over 2. So what I would write then as my actual answer is like this. Okay, I don't want to just leave it as y equals x plus 1 over 2 because that doesn't even answer our question, right? So if my function is 2x minus 1, my inverse, which is this f with this negative 1 up there, kind of looks like an exponent, but it's not. F with an inverse like that is a negative 1 of x is x plus 1 over 2, or any of the equivalent forms. Now note that this is the standard notation for inverse, okay? Inverse of a function, but that's not the same as f of x raised to the negative 1 power. That would be like this. The whole thing raised to the negative 1 is not the same, okay? So we like this one, we don't like that one, and that's because this is 1 over f of x. So like when you have 5 to the negative 1 power, that's 1 over 5, right? So f of x, like 2x minus 1 to the negative 1 power, is 1 over 2x minus 1. But this is my inverse, f of inverse, or f inverse, not f of inverse, f inverse of x is x plus 1 over 2. Okay, so now if we have y equals x plus 1 over 2, that will take me from this side back to this side. And let's try it. So if we have, let's say 1 plus 1 is 2, divided by 2 gives me 1. And in this case, because it's fractions, you do the whole top thing first before dividing. So you do like 3 plus 1 is 4 first, then divided by 2 to give you 2. 5 plus 1 is 6, divided by 2 is 3. Negative 3 plus 1 is negative 2, divided by 2 is negative 1. Negative 1 plus 1 is 0, divided by 2 is 0. So this is my decoder. It's my reverse, inverse, however you want to put it. So if I give you this secret code, and then you can solve for this secret code to give me something back over the cute washi tape wall. So when I said like whether or not an inverse exists, it has to do with the fact that we hope that our inverse is also a function, and if that is a function, then we kind of need to do the opposite of the first rule with the vertical line test. Now we need all of our outputs which are now inputs to our inverse, to have one clear output, which is actually our original input, if that makes sense, because we switched our x and y's. So this side, I guess I should use the word, but all the possible values for x, our inputs, is called the domain. You may have heard of it before. And all the possible y values is called the range. So in order for this to exist, this inverse to exist, is that before we have domain and range, but now the original function's range is now our inverse's domain. It's kind of cute, but our range becomes our domain going back the other way. And so in order for the inverse to be a function, we still need the same definition, that each input has one clear output, which means that each of the original inputs needs to go to a unique output. Okay, so that practically speaking, means that with the original function we had the vertical line test, but now we also have a thing called the horizontal line test, which is just drawing horizontal lines, which is to set y or outputs constant, and that should only intersect our function at exactly one point, which is a unique x as well. So I hope that makes sense. I know it sounds kind of complicated because we're switching x's and y's, but essentially if you're going from input to output and then you do the inverse, the original outputs become your inputs now, and your original inputs become your outputs now. So in order to follow our definitions of a function, in order for our inverse function to actually also be a function, we need the horizontal line test as well. But let's say you don't know that ahead of time, or you don't feel like graphing it or whatever. What you can also do is go ahead and do the flip-flop of x's and y's, and as you're solving for y and you're isolating it in terms of x, sometimes you'll just get multiple answers. You just have to be aware of what kind of function you're working with. A lot of times you run into issues with like squares, like if you have x squared, or even powers, even exponents, or trig functions, for instance, right? So as you undo it, so to speak, you might end up with like a plus or minus square root of something, which gives you kind of the idea that there's going to be multiple functions here, so then that would not exist. Or alternatively, what ends up happening with stuff like inverse sine or inverse cosine and stuff like that is that you end up limiting your original function over a smaller domain, just so that you can still study the function or the inverse of a function, but you just restrict it over a smaller domain or range, so that you can still kind of study the properties of an inverse without running into problems with the vertical line test. So what you can do is just go ahead and flip-flop it, and then see if you end up with one or two or multiple functions here. And if you end up with like a plus or minus square root or something, either restrict the domain depending on the question, or you just say that the inverse function doesn't exist because it's not a function. Okay, so I hope that that's helpful for now, just a little intro. One other thing that's coming up in my mind is that graphically, what we're really doing is, with our pictures, right? So in this case, a line, when we swap x and y, what we're actually doing is reflecting our graph across this line that's y equals x, because we're flip-flopping y and x, right? So we're basically reflecting whatever picture we have across this line y equals x, which is if we have the horizontal x-axis and the vertical y-axis, then y equals x is the 45-degree straight line from going from left up, bottom left up to the top right. It's 45 degrees. And so when we reflect it, we're kind of switching the x and y coordinates, because when we graph things, it's always x comma y, so it's left and right depending on if it's positive or negative, and then up or down depending on if it's positive or negative or 0. So when we flip-flop and we reflect it across, it's like folding it down across that line. So everything that's above it goes across, everything below it goes across back up. It's because we're interchanging those values, so that what was y is now x, and what was x is now y. We can do that another time. We can definitely get some graph paper and draw this out, but just for this linear case even, we can see that this is a line of slope 2, so it's steeper than our y equals x, so it's going to be up here. It has an y-intercept at 0, -1, so that's where it touches the y-axis. But the inverse is going to be this, which is where you'll want to distribute this to, it's 1/2 x plus 1/2. So 1/2 x is going to have a slope. It's positive still, but it's flatter, right? And it's going to have the y-intercept at 1/2. So you have a sharper one and you're going to have a flatter one, and that it's going to be hard to see now, but that's reflected across this y equals x. So, whoops. But before I draw all over myself trying to demonstrate it, we can definitely do this on graph paper sometime, but you can kind of take some time to check that out if you're still awake and interested. But if not, I hope that you are having some sweet, sweet mathy dreams, or if you're ready to get going with the rest of your day, I hope that you have a wonderful rest of your day. I'll see you around for more math very, very